by hybrid model, we just mean that you're combining several parallel programming models, or maybe I should in fact say systems, because most of the things that we use today are themselves combinations of multiple, what at least a theoretician would consider a programming model. So for example, MPI is not just message passing, it includes other sorts of programming models in a bigger programming system. And you may mix this in the same source, you may have combinations of components. Typically, when people talk about the hybrid programming models in parallel computing in the technical environment, they're talking about MPI and Threads, or almost, in most cases, really, MPI and OpenMP. There are others. There are some interesting other choices to think about, which I would not think about for production code, but I certainly would think about in terms of research, or in terms of moving forward for what you might use for more extreme scale systems. And I want to point out, some people sort of feel, well, I really want a single programming system. I don't want to have to learn two things. Everything should be simple and together. And well, if you're using MPI, you're already using a hybrid system because you've combined MPI with C or MPI with Fortran. That is a hybrid system. And it becomes more so as both C and Fortran now provide explicit access to different kinds of parallelism. So C11 has thread parallelism built into it. Fortran with 2008 has distributed memory parallelism built into it through co-rays. And we have users on our systems who are making use of that, as well as MPI. And lots of applications are multilingual. Lots of people use, for example, Python to stitch together their codes, or in fact, they may use Python for their entire code, except for some little pieces done in C and Fortran. And this is not a bad thing. The reason people use those multilingual environments is because each language provides them what they need. They provide some more productivity, more effectiveness for that part of the task that they're doing. And so, as we've learned in most other areas of engineering, the way you put together a really workable system is you put together the right parts and you make them work smoothly together. And this will be part of the theme for this section, is that the real challenge in the hybrid programming models is not the individual pieces or learning two things. The real challenge is making them work together smoothly. This is a place where much remains to be done. At extreme scale, we're going to see more and more of a demand to have our programming systems that are optimized for those pieces of the system that we have. It's really unrealistic to expect to come up with a system that would allow us to cleanly and efficiently use resources spanning very tiny cores and processing near memory all the way through systems made up of 200 to 500 cabinets. In theory, you could do that by using a suitably smart compiler, but I will indirect reference previous comments about compilers. So MPI describes parallelism between processes. So, and each process has a separate address space. As you've already heard, thread parallelism gives you a shared memory model. So you have an address space, but you have multiple program counters effectively. OpenMP and P-threads are really common models. How many people use P-threads? Okay. That's a lot of fun, isn't it? This is why you should learn OpenMP. There's also a wonderful article on why threads cannot be implemented as a library, which I also encourage you to search for and read. There are a lot of subtle issues in the interaction of threads with languages that mean that the only safe way to make use of threads is within the language, not within a library that is called by the language. That article will give you some nice examples of why you really need to have something that's integrated with the language like OpenMP. Okay. Now, when you're programming multicore, it's the case today that almost all chips are multicore. Now, Some of you might say, well, aren't they all multi-core? There are some for particularly demanding applications which have quite old architectures but are really reliable. So if you're trying to run a processor in deep space in a high radiation environment, you don't really want to have a multi-core processor. And they still make CDP 1802s, surprisingly enough. But most of the ones that you're going to encounter have more than 4 cores or more, possibly moving into the hundreds of cores. And our systems today are made up of these. And as I showed yesterday, the fact that things are made out of these multi-core processors, it even changes the way you have to think about these machines, even quite abstractly. The sort of mental model you have for the performance and the behavior of the system can no longer pretend that a multi-core processor is simply a bunch of separate processors that operate independently. They share resources, and there are never enough resources to go around. When these things are programmed, we've talked about using MPI. This is still a very popular way to program even these multi-core systems, and there are good reasons for that, and we'll say a little bit about that a little later. There are more and more applications, however, that are using this hybrid model, the MPI plus OpenMP, and some are using MPI plus pthreads. Using pthreads gives you a little more control over what's going on, but at a significant complexity in that you have to manage a lot of the stuff that OpenMP would do for you. So there are quite a few myths. I'm sort of hoping that these myths are fading, but over the last, say, decade, we'd hear lots of these things. So for example, the hybrid model just never works. That it's always faster to do MPI everywhere. And it's a myth. There are examples, you can find them in literature, where people have been able to demonstrate improved performance by using the hybrid model. Some easy examples are from areas like finite element assembly, where you're able to take advantage of this hybrid model using OpenMP to get better performance. Of course, there are other people who say, well, the hybrid model always works. And there are a number of examples where that is also false, where the performance that one achieved with one process per core beat what people were seeing with hybrid models. And some of that is related to the quality of the implementations, the quality of the programming. Some of the issues that you heard about this morning can have a big impact on whether using the hybrid model will work well. Another comment that's sometimes made, and we touched a little bit on this yesterday, is that you sort of need a special thread-safe MPI. Technically, that's true, that you do need a MPI that's at the level of at least MPI thread funneled, but in reality, all MPIs are good enough to use with this level of, particularly the OpenMP level of thread parallelism, effectively because the few corner places where this would matter, the runtimes and operating environments have already adopted approaches that are as thread safe as necessary. And then maybe the most serious one is people say, well, this has got to be too hard to program. And my first reaction is, harder than what? Harder is a relative term. And yes, okay, this may be harder than you would like, if that's your, but harder than what what are your alternatives? In fact, the way we solve hard problems is we decompose them into a collection of smaller problems, which we hope are easier to solve. And in the case where putting them together to solve the overall problem doesn't add too much more complexity. And in many cases, the hybrid model lets you do exactly that. So you need to get more performance on the node. You'd like to exploit the fact that you have a shared memory node. why don't you use a programming model that's designed for and optimized for programming a shared memory node? You've got to program separate nodes that don't share memory, that have to use message passing or remote direct memory access to move data around. Why don't you use a programming model that's been optimized for that? And then put them together. Do that instead of saying, I want one programming model that will let me do all of that. You can have such programming models. They're nice and elegant. I remember using one many, many years ago. People said, this is really great. I was able to write this LU factorization in 20 lines, and it ran and produced the right answer. And sounds great, right? Why aren't we using this? Well, I timed the performance. It was an astounding 50 kiloflops on an entire CM2. So it was elegant, but incredibly slow. How many of you like writing parallel programs, just like for fun? Okay, yeah, those are exactly the two people who put their hands up, right? The rest of you are doing this because you need to get something done, and the machines aren't fast enough with a single core, right? So the goal of writing these parallel programs is to get a code that is fast enough to answer the question you're asking, do the science that you're asking, right? So you have to be able to get that performance. Having the elegance, having the simplicity without getting the performance doesn't accomplish the task. So that's part of this. It's harder than program, harder than what? If your goal is to get performance, then you want to put together the right collection of tools to let you get that performance. And in many cases, getting specialized tools for each piece and putting them together is going to give you the right answer. Okay. Since these myths are neither true nor entirely false, it is important to be paying attention to this. I do want to mention this book. This book is now a bit out of date because OpenMP has continued to evolve and improve, but there's still a lot of relevant, useful information, particularly for programming for performance and for the hybrid model. So this is another place to look for information on using OpenMP in this sort of hybrid environment. So let me go back to saying a little bit about the MPI levels of thread safety. So MPI was originally designed to be thread safe. So the original MPI-1 was designed to be thread safe. There were some other message passing programming models at the time that, for example, had the concept of a current message. Current message, current anything is a concept that's really not thread safe. It's current for whom. But allow it to work with a multi-threaded environment because we expected threads to become important. As we were doing MPI-2, IBM did a thread-safe MPI implementation, and they discovered something which was, I think, underappreciated by in fact, the general computing community, and which is still true today, which is that thread safety is a bear. And thread safety is not cheap. So if you having thread safety means that you pay a performance penalty. You get something for that, but it's not free. And they realized that there were a number of steps where they had to do a little bit more work, a little bit more overhead, but you got a little bit more thread safetiness. And because of their experience, we put in these 4 levels of thread safety and a way in MPI. So MPI init was the MPI-1 way of initializing MPI for a program. We added an MPI init thread. So if you do MPI init, you get MPI with the lowest level of thread safety. If you need anything higher, you should use MPI init. And it has these 4 levels of thread safety. So thread single is there's one thread, and that's it, as far as the user can tell. Thread funneled is the case where there are multiple threads, but only the main thread, the thread that called MPI init thread, the one that called MPI and Thread, that's the only one that makes MPI calls. And that's important because that means that there are no memory consistency issues for the MPI code there, because it's always the same thread that's accessing anything that has to do with MPI. Thread serialized, the user promises that only one thread at a time makes MPI calls, but it may not be the same thread from time to time. That, the difference there means that the implementation has to be a little bit more careful of some subtle memory issues because different threads may be touching different parts of memory. And then MPI thread multiple is the free-for-all. Multiple threads can be making MPI calls at the same time, and who knows what's going on. And so in that case, the implementation has to work even harder to ensure that it behaves correctly. Particularly if you want to use thread multiple, or you want to do task parallelism where the different tasks may mimic MPI calls, you must use MPI init thread. It has, in C it has 4 arguments. In Fortran, it only has these 2, whereas in Fortran, MPI init it has 3. MPI init has just the error argument. So it's the same pointers to argc and pointer to argv. You say what level of thread safety you want, and you get back what you got. And just like this morning, where you can ask for a number of threads, but you may not get them, you can ask for a certain level of thread safety, you may not get that. You might get more, you might get less. So in fact, what's most likely to happen is that you will either get MPI thread funneled or MPI thread multiple in the current implementation. So if you ask, for example, MPI thread serialized, you'll probably get back thread multiple. Just because that's what people have sort of settled on. In many cases, so for example, the default build for MPI-CH is thread multiple, but if you don't ask for thread multiple, it doesn't execute all of that thread safety stuff. So there's an extra branch basically at the beginning of each routine that says, what is my level of thread safety that I've been told to go for high enough that I need to do this extra thread safety stuff. So his branches are somewhat costly, but they're cheap compared to the stuff that you have to do for thread safety. So the cost is fairly low. So what does it mean when you do that? So MPI also defined what it means to be a multi-threaded program. So if you've got multiple threads that are making MPI calls concurrently, the outcome will be as if you did some interleaving of those calls. And that's the same definition that pthreads uses for making, for example, non-pthread, making pthreads calls. Also, and this is a little stronger than what some thread environments give you, all of the blocking MPI calls block only the thread. They don't block the process. So you can set up 2 threads, and you can put a blocking receive in one, and the other thread will keep running. The other thread could do blocking send. In fact, you could do a blocking send to itself, and it would be received by that other thread. There are places, though, because of this arbitrary interleaving, it's possible that when you write the code, you might get to one of these race conditions where, for example, you say you have 2 threads communicating on the same communicator, and then when they're done, one of them frees the communicator. Well, it's your responsibility as a programmer to make sure that the other thread is done using that communicator before it gets freed by the other thread. And so it's not MPI's responsibility to even detect that you did something evil. You just have to do it right. Similarly, collective operations, MPI requires that a sequence of collective operations on the same communicator be the same in all the processes participating in that communicator. If you have multiple threads, then you have to be very careful as they're calling collective routines to make sure that you maintain that property, because that's a property across processes, not threads. So typically, if you're using MPI communication in the thread multiple and using collectives, one recommendation is to use a different communicator in each thread. MPI implementations are not required to support thread multiple. This is another thing that came out of IBM's work, was that delivering their MPI implementation on time in a way that was correct for multiple threads and fast. It's that old joke about, fast, on time, and correct, pick at most 2. Right? So sometimes it's pick 2, but I've learned it's really pick at most 2. Maybe sometimes you only get to pick maybe 1. It's just hard. And so a lot of applications don't require multi-threaded MPIs. It was again the sort of case where we would love to have defined a message passing interface that was mandated to be supported within C and within Fortran. That would have made the data type stuff a lot easier. We don't have that kind of influence over the general computing community. So the same thing is true here. We can't force vendors to provide something that's going to be very difficult and hard for them. So we try to shame them into providing multi-threaded implementations. And at this point, we're pretty close to being there. But the standard only requires the basic level, the thread single. And if you call MPI init instead of MPI init thread, the standard, it says here you should assume that you have only thread single. The standard says that you must only have thread single. So if you're doing anything with threads, be nice and use the init thread. So of course, even if they say that they're thread single, or you called MPI init, so it's forced to say that it's thread single, it's really thread funneled. You should be able to use at least the loop level or loop style parallelism from OpenMP without doing anything else. This is what people typically do. And while technically not correct, I don't know a single example where it won't work. The other interesting thing is that these 4 levels can be mapped pretty directly onto specific levels of OpenMP parallelism. So, well, thread single is no OpenMP. Thread funneled is the examples you've seen this morning, where you've got a program and you've got some loops, and the loops do something, but there are no MPI calls in the loops. Thread serialized would make use of an OMP single, for example, which says only one thread at a time can execute this code. It's often there are things that you sometimes need to do like this, output, for example. MPI calls fit in there. And then, of course, sticking an MPI call inside something that's going to be managed in multiple threads by OpenMP is the thread multiple case. For performance, you're making sure that you're close to memory, making sure that you stay in the same place that you're at. It's one of the reasons why the old MPI programs often work very well, is they maintain this locality. OpenMP before version 4 had no such affinity. 4.0 adds, if I've got this right, thread affinity, proc affinity. And there's a lot of discussion of finding ways to provide explicit memory affinity control. So I think over time this will improve. But it can be a real challenge. And you may read about things like first touch. If you have multiple threads accessing memory, that memory can get assigned in certain ways that get mapped to the different bits of hardware. It's often important to have the thread that's going to be doing most of the work on that memory be the first one to touch it, because otherwise it might end up in the wrong place. It's a weaker form of the false sharing that you saw this morning, but can have the same sort of performance impact. A problem with that is this usually depends on a static mapping. So if things are more dynamic, you can end up with stuff in the wrong place over time. And any shared memory system has dragons in it. And OpenMP is no exception. And so there are occasionally places where you may need to be careful. And in fact, there's discussion about lock-free algorithms. I love lock-free algorithms, but I'm with Tim. They're extraordinarily tricky. And having, in fact, made a published mistake with one, which nobody caught, and no human being ever caught. Right? It was caught, however, by a theorem-proving system. So that was how subtle it was. But they are hard. So you do have to watch for those things. More serious, it's really this bit about how do they work together. And right now, right, I was arguing the benefit of having a hybrid model is each piece can be specialized for its environment. The problem is that underneath, they have to share some of the same resources. They don't really negotiate very well on that resource sharing. There's been some discussions about addressing this problem, but it remains an issue that you can sometimes run into. Again, I think the systems are getting better and better over time in terms of not tromping on each other and causing lots of problems. If you go back and look at some of the older papers in the hybrid model, some people got truly terrible results, sometimes traceable to this, the fact that OpenMP and MPI both believed that they had total, complete ownership of all the resources, every single core, every single cycle, and they ended up fighting over those cycles, and the user was the victim, because things would, they'd spend all their time pounding on the same resource without making much progress. And it's not just the cores, you can have memory bandwidth, and another piece of this, and I'll show some data, it's a little old, but it remains very true, is the apportionment of the network resources by the systems tends to be by process, not by thread. It's sort of just the way it is. It's a decision by the operating system. And that means that if you have too few processes, you may not get enough memory bandwidth or enough network bandwidth. So there are, however, a lot of places where this works well. Compute-bound loops, particularly when you've got lots of operations per memory reference. Fine-grained parallelism, the overheads, the latencies in message passing, even the overhead and latencies in the RMA mean that algorithms that have a very fine-grained structure that need to coordinate with the other threads, processes, whatever, on a very frequent basis are really impractical. So, for example, if you wanted to do an incomplete factorization preconditioner across all the cores on a chip using MPI, I would just tell you don't do that. Because the overheads of implementing that algorithm with such fine-grained synchronization is just going to overwhelm any benefit you get from it. In a shared memory model, you've got a chance. Not a new guarantee, but it's no longer completely out of the question. And so the hybrid model gives you this nice access to some fine-grained parallelism. Load balancing is another one. Again, as Pete mentioned on Monday, performance predictability is something that's fading. And you need strategies for load balancing. That usually means moving work around, which means moving data. In a message passing environment, that means packaging it up and sending it. In a shared memory environment, it may be as simple as simply letting somebody else discover the data. And then you can allow the hardware, the shared memory hardware, to move the data around. Loops that involve a lot of operations per memory. And the reason I say this is one of those resources that you don't have enough of is memory bandwidth. One of the things that you can find as you use lots of threads on a multi-core processor, if they're doing almost nothing but reading and writing from memory, you reach a point where you can't get more performance. And that's because you've reached the point where you cannot move data in and out of the chip fast enough. So you need to, one of the places where you can take advantage of this for these sort of compute bound loops is where you're not strangled by that memory. Now you can bring extra cores to bear on that computation. For the fine-grained parallelism, so in this case, even if it's memory bound, in the fine-grained parallelism, you're really bound as much by the coordination, the synchronization in that fine-grained parallelism as you are from memory references. So having this can really help. Load balancing, again, for example, OpenMP has some built-in features to support dynamic scheduling so that it can adapt transparently to a load imbalance, caused by any kind of any source of performance unpredictability. In fine-grained cases, you might want to lower the overheads. You can do that by having combinations of static and dynamic. Again, I think Pete alluded to that Monday, in that making everything completely dynamic has extra overheads, but that doesn't mean that you have to pick endpoints. You can pick combinations of static plus dynamic that give you good performance. Another nice place, and in fact, somebody mentioned this to me yesterday, that they have a table of data that all their processes access, and it's the same table. And in the MPI everywhere model, every process has a copy of that table. Uses up extra memory. Memory is getting scarcer on these big systems. You can take advantage of having a single shared table. Now, of course, you'll have multiple copies of the table because you have cache, but you only have copies of the part that you're working with. Some memory-bound loops also work well in this model by reducing your total memory use. It also reduces the total memory pressure on the memory channel. Where's pure MPI better? If you really need to manage locality, you're really very bandwidth bound. In some cases, just sticking with single processes, single threads that are looking at just a strip through the system and being very careful to manage locality will do as well as you can do with anything. That the extra benefits that you might get from having multiple threads doesn't cover the extra overhead of managing those extra threads. Another reason to use at least multiple MPI processes, so instead of using one MPI process per chip and node, you may need to use multiple MPI processes. Again, it may take multiple processes to get full bandwidth out of the interconnect. And if you're constrained in your scalability and your performance of your application by the rate at which you can move data between the nodes, then you may need to have parallelism in the units that can talk to the interconnect. And we did a couple of examples. So we have what are effectively two identical cases. So we've got, in both cases, we've got 4 threads talking to 4 threads. In one case, we have one process with 4 threads. In another case, we have 4 processes, each with 1 thread. And so, in some sense, in any sense, you would like it to be true that the performance of these two situations was identical. They're doing the same thing. One thread is sending to one thread. And yet, that's not what we see. Here's a couple of examples. These are a bit old, but we still see things similar to this. So this is an old version of MPI Stage 2 was pretty much the same. An old version of OpenMPI was pretty much the same, except when you had 8 threads to 8 threads. And then these were 2 commercial versions. So this is bandwidth. So up is good. This is 4 processes to 4 processes. This is 1 process with 4 threads to 1 process with 4 threads. 8 processes, 8 threads. 4 threads, processes, threads. Okay, yeah, so here are all those bad numbers. Also, locality is critical, so you need to be paying attention to the placement of processes. We talked a little bit about the topology issues on the network, the topology issues with respect to the MPI processes. You also have to do this within a node or within even a shared memory region. So you can think about, here we have a 2-chip, each chip with 4 cores. If I enumerate the threads or the processes, either one, in, say, a round-robin fashion. So I put first one on this chip, then on this chip, then on this chip, then on this chip, then on this chip, this, and this. Sort of a nice way to distribute my threads across the resources. But if they're now communicating with a regular mesh, so that think of these numbers that I put in here are the mesh coordinates that correspond to those threads. If I sort of think of them as I'm just going to take the consecutive threads, map them into a mesh, that means that this one's going to be sending over here, this one's going to be sending over here, this one will be sending here, and so forth. What that means is I have 3 times as much data crossing this boundary between the chips as I would if instead I had this process talking to this one, or this thread talking to this one, this thread talking to this one, and so forth. So depending on how I do that layout, I can have an enormous effect on the amount of data that has to move over links that may be slower than some of the other choices. So moving between chips is almost always much slower than moving data within the chip. And the factors are integer multiples, typically. And so a bad mapping won't be 10% worse, it'll be a factor of 2 worse, or in this case, a factor of 3 worse. And so getting the wrong mapping as you're moving the data can have a huge effect on your performance. There are a number, yes?
So in that example, how can a user easily say, I want this graph to be here, I want that graph to be that chip?
So it used to be hard in the sense that there was no portable way to do it. So with OpenMP 4, there are mechanisms to bind the threads to the resource. So you can avoid the problem of having the thread bound in the wrong place. And you can find out, I think, where it's bound. So you can figure out the mapping to some extent. So you should go read about that. It still doesn't help with some of the memory placement issues, but you can control this. That's assuming, of course, that the operating system allows you to do that. Right? I don't know what OS X does, because it seems to be belligerent about not letting you know anything. Yes?
HWLOC has been mentioned, and I would highly recommend starting to use it and understand it, because it gives you not just the simplistic view of map something, but the hierarchical view that you can use in your application.
So I wish I could, no, okay. I'm going to mention the OpenMP part, because OpenMP, at least this part of the placement is part of the standard. I like the idea behind HWLOC. I've used HWLOC. Sometimes I've been really happy. Sometimes I've been miserable. And part of it is that the documentation is terrible. Some of the features in HWLOC are hard to support, but you can find out that they're not, the implementation doesn't give you enough information that they're not supported. In some cases, I had to go read the code. Oh, of course, I can go read the code. The one thing I would say is, what you shouldn't do is write your own replacement for HWLOC. But I would say, first, try what's standard. Second, try HWLOC. but be careful. And then third, there's some things you'll just have to fight with. Okay, so for example, HWLoc is quite happy to tell me stuff about my Mac that are false, so because the Mac won't let anybody know what's going on. So.
Oh, well, actually, affinities, I think, are not supported by the by the OS X kernel.
Exactly, but HWLoc is happy to tell me stuff that's not quite true. Right, so. Well, and just as sort of as sort of software engineering aside, HWLoc uses Doxygen for its documentation. So I have nothing against Doxygen, except that one thing is that it lets people produce documentation without actually writing anything, and that documentation is worthless. Doxygen potentially gives you a good framework in which you could provide good documentation, but using Doxygen over source files to produce your documentation is a hostile act. Okay, so, and it's one of the problems with HWLoc, because you really have to go read the source files because there's no documentation that's worth anything. And I wish I wasn't saying that, because the concept behind HWLoc is right. It just needs to be done better. Okay, so this is one thing to be careful of, and so the two affinities are important. Affinity of the threads to cores is important, so that you understand these issues, and it's very similar to the node topology issues we talked about yesterday. Memory affinity issues can also be very important. And that's an area where there's still no good standard mechanism. So we'll keep waiting. There are a number of ways to do hybrid programming, other ways to sort of think about it. Yes?
Just a quick question before that.
Yeah.
Let's assume that HWLoc is bad. It's really bad. I have a machine with 4 sockets, and I want to run 1 rank per socket, OpenMP within the socket, and I want the best binding of the ranks to sockets, threads in the right order. How would you do it?
I'd probably call HWLoc and suffer.
Because if I can...
Wait, I'm sorry, I wasn't listening to the question. What do you want to do?
N ranks and N sockets and threads within the socket.
A lot of it depends on how you're... So a properly done resource manager will provide you a mechanism to confine your MPI process to a socket.
Okay.
Swarm does that on our systems at Livermore, at least.
Kind of. You can't tell Slurm to bind each thread to a hardware thread, for instance.
I'm going to back up and say that the real answer right now, the real answer depends on the precise environment you have. So on our Cray, we have a different set of things that works well.
So I forgot to mention a portable way.
Yeah, and the answer to that is no. There just isn't one.
Right.
One of the reasons that I pushed the OpenMP solution first for the thread binding is it would answer the portability thing. The situation is not as good as we would like it to be, but the important thing to note is it's better than it was 2 years ago, and I expect it to keep getting better.
I mean, Bill's right, but the right way to get a portable solution is to push your resource managers to provide you a mechanism by which you can say, confine me to this domain of cores. And when they do that, they will pass that domain of cores to OpenMP as the list of places on which OpenMP threads can execute. And then your OpenMP threads will confine themselves to that.
So I think the two of you should talk during the break. Because I think for the class, the content is, this is a contentious issue and a difficult one. Okay, so I just wanted to close it. A number of ways to think about putting together these hybrid programs. One way to look at it is whether it's arranged as a fine-grained model where the program is really single-threaded except where it actively uses multiple threads. So the nice thing about this is you can take your MPI program and make it multi-threaded easily. But there are lots of cons. You get overhead in managing the thread pools. Particularly the memory affinity can be an issue because you can end up with different threads getting affinity to the same memory. And of course, you've got all these serial sections, so that limits the amount of performance you can get. Still, in some cases, this is not necessarily a bad way to go, particularly if, even though it's fine-grained, there's very little that's going on that's outside of the fine grain. An alternative is the coarse grain model. This is sort of like main, and then you do OpenMP parallel, and you blah, 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 and you close that, and you exit the program. So benefit here, of course, is you've got much less overhead for all of these things, including once you've set up the locality and the memory affinity, it's persistent, and it is forcing you to think parallel from the beginning as opposed to pretending everything is serial except we're making it faster. The downside is it's harder. You have to think carefully about larger blocks of the code and their blends and so forth, of course. For the programming models, and it's just sort of in summary as we're trying to think about these hybrid models, one of the big challenges is coordinating among the resources. Today, you do this partly by relying on the implementers knowing that they're probably working with MPI or OpenMP, trying to find ways to stay out of each other's way, as well as being cognizant that this issue exists. You have to remember these things about, there are all of these resources, memory bandwidth, access to the cores, access to the interconnect, which are going to be shared among the running processes and threads, and it might not be shared fairly. The operating system's another antagonist in many cases that may not do what you want. On systems like Vesta, like large crays, the operating systems have been tuned for scientific workloads. They tend to schedule things the way you expect. For the broader community, the way they use threads, the way they use processes is very different than the way a lot of scientific applications use processes and threads. And the scheduling strategies that are appropriate and optimal for them are often exactly what you do not want to do. And so you can run into some of those issues as well, particularly when you're using a commodity cluster. So as we go forward and try to figure out how to put these things together, figuring out how to get this coordination of the resource is going to be really tricky and important. I think that's where there's a lot of research opportunities. In the short run, for those of you who are trying to write these codes, understanding that that can be the source of some of the problems, that this decision over who has access to what resource can be critical. So for example, if you tell the MPI implementation that you want asynchronous progress, well, this doesn't happen by a magic progress fairy. It happens because there's a bit of code that runs on in a thread on a core somewhere. And if you then also say, well, I have a 4-core processor, and I'm going to run 4 OpenMP threads on it, and I'm going to do static blocking to keep the overheads down, you're going to get absolutely awful performance because you don't really have 4 threads. Well, you have 4 threads, you don't have 4 cores for them, because there's 1 core at least that's being shared by the MPI progress thread and your OpenMP threads. And so keep that in mind as you look at the design of your code, design of the algorithm, and the performance that you start seeing. There has also been a lot of work that's been looking at sharing communication infrastructures. This is a really hard problem. It's one of those things that we all think is a great idea in principle. Execution is very, very difficult. So mentioned a couple of examples up here. It's possible, but to date, it has proven elusive to put together such a resource that would allow these different programming models to sort of sit upon a common underlayer, which would then solve these problems. And I think in the end, we're going to discover that they're going to have to be peers that negotiate as opposed to all being children of the same controlling system. In conclusion, despite some of the complexities, I think hybrid programming models are often the right way to go. They exploit sort of complementary strengths. They allow you to focus on making the best use of certain kinds of hardware resources. There are pretty good evolutionary paths to these, so you can start your code with whichever part you think is going to dominate the design. And this is often the distributed memory part because the complexity of the data structures for distributed memory codes often dominates the design and implementation costs. So you do the MPI part first, then you can use OpenMP or another hybrid model to get more performance out of the individual cores. You may, at that point, change some of the designs to take advantage of having a lot of shared memory to put some of the data structures that are shared into shared memory. Longer terms, I think we're going to see these issues addressed, particularly the ones of negotiating resources. So maybe in 10 years, as an optimist in me, we will see programming systems that efficiently share these communication resources and effectively negotiate the sharing of those resources with each other. The short form of this is hybrid programming is good. It's the way we do engineering. And it's not that hard. And in fact, it's probably easier than the alternative in terms of getting the most performance out of the system. Any questions? Yes?
In your 4-process versus the 4-thread slide, share with us a little bit more insight why the 4-process case generally speaks more bandwidth.
To answer that, I would have to have understood why the resources were allocated that way. The hypothesis is that the operating system is only granting access by the processes to this shared resource, and so there's a limit to how much each process gets out of the resource. And if there's one process, it can't monopolize the resource. So if, for example, the operating system says, I'm only going to let you have half of the bandwidth, then that's it. Threads and processes are not identical. There's more that goes on there than just the scheduling.